Hello. It's just over midnight, Sunday morning. I was to a birthday party yesterday afternoon, and when I came home I slept for 4 hours, but now I'm up and around again. Now first we are in the whole group, and the modular forms there are just the all the lattices. So we are working on all the relevant sublattices of span Z and 1 when we are computing the modular points. So that should be simple. No lattices need to be excluded. But before doing this, I wanted to make a dry run, finding out how to compute it in Maple. So I made a dry run with the M12. It should actually be M here, because I do use delta, but also the forms of weight 12. Now, first we define the delta function up to q to 20th, and then take out the coefficients. Yeah. And they are well known to us, 1 minus 24, 2, and that's it. Actually, this one's the only one I knew, but we've seen them before. And then I test that they are correct by one of the results, that the tau of n minus the sum of divisors of n to the 11th vanishes modulo 691, and they do. That's a good consistency check. Next, we should find the series of, I actually thought Eisenstein series here, but that's not what it is. It's the square of E6. And then we take out the coefficients again. The reason I used this was because we have integer coefficients. Right. So first I want to compute T2, and I actually went back to the to write up what are all the lattices we work on. And that's what we've got. And these two give this, and the other part comes from this, because f of, I shouldn't have written span. There we take 1/2 out. And that's just 2 to the 12th f of z. This is, of course, all the formula 515 with capital N equals unity. But I needed to work through this once again. This one only take the even coefficients and put, say, a4 is mapped to coefficient of q squared. And that's what happens here. And this guy doubles the coefficient, and that means it's only when n is a multiple of 2 that we get a coefficient. And that's what's defined up here, that if 2 doesn't divide n, if it's not a multiple of 2, then it's naught. Otherwise, it's the coefficient of n half. First I wrote n half here, but then I got into programming problems, which we don't want to talk about. All right, we now do this on the delta function, T2 of delta I call it. And that's actually minus 24 times the delta function. And we knew in advance that it would be an eigenfunction, and the eigenvalue is minus 24. And then I'm ready to do the same with E6 squared. I call it E21 for not wanting to call it E12, of course. It's 2049 times b, and we already knew that that should be the value of the Eisenstein series, or the eigenvalue of the Eisenstein series, being 2 to 11th plus 1. That's one of the theorems. So we subtract to see the difference, yeah? And this is what we get. And then this should be 2,286,144 times the delta function. So we just multiply this with the delta function and see that they actually do agree. This equals this, etc. And that means that we have the operator T2 in the basis of E21 and delta. And then I did a little work to find a formula for the coefficient so that E21 plus c times the delta function is an eigenfunction. And when I saw that, I said, we knew that E21 was the eigenfunction. It's an Eisenstein series because it has the right coefficients. Just checked that this had to be the one. We recognized this one probably, but I needed to check them all. So we wrote down the first terms of E12, and they agree nicely. My plan was to do T3 and then T4, but T3, that would just be the same, no new insights really. T2 and T3 commute, so no problem. Then T4, I did have a little caveat there. When we square T2, we get the lattice spanned by set halves and 1/2 twice. You can see here if we operate with 1/2 on 1 and on z, then we get that twice. But it's only 1 in T4, so we have to subtract it. It's called T22 as far as I remember, of whatever lattice we started with. But what does it actually do? And then we take 1/2 out. And that's just f. That f is an eigenvalue of T22 as well. So when it is to T2, then it will be to T2 squared and then to the difference as well. So it's an eigenvalue of T4 as well. So I thought now I'm ready to start on this problem. And we will be, we can actually see this F1, that's delta squared. So we can start on A, delta squared, that starts with Q squared minus, and then twice the product, that's 48 Q to the third. And now if we operate with on T2, then we do get Q now I wrote this formula up here. Here we have it. It's f of z halves. It's not clear. Well, so I'll just find the right formula in the book and write its number, and then it should be clear. So what I'll do now is to find the expressions for this, or the series for these functions in Maple, so we don't just have the first two terms, which are basically all we need, but we'll verify the result that it fits with the higher terms as well, because it's no problem. Hello again. It's now 2 o'clock in the morning, 4th of February 2024, and I've done what I said I would do, and one of the things was to find this formula that is actually proposition 32, and the formula is 555. And I made a mistake, because if this is the modular point, then T2L is 1/2 this, plus 1/2 this, plus 1/2 this. But T22.2 of L equals 1/4. It's n squared, and therefore we get a factor n down here, which I missed. Well, so that's a little detail. Now, we set the weight to 24 and use 16 coefficients. I expect them to be rather large, so let's not make too many, but neither too few. And I define f delta squared, q squared times this product to 48th, and then take out the coefficients, and that was q squared minus 48q to the third, which is what I claimed here, fortunately. And then E6 squared times delta. This is E6 squared, and then delta comes, and I take out the coefficients and call them G. We see that this guy is actually normalized. Whereas this cannot be. Then we start T2, the same definition as before. T2 of F comes out normalized, so we just subtract G itself to get this, and that turns out to be 2112 times F, which we see here, all the coefficient agree. And next T2 of G, it's minus 1032, so we add that times G and get these coefficients, and they should be this times F. So let's see, and I shouldn't have taken all those, but the first ones agree. That means we can write up the matrix, which I've done here. F is mapped to 2112 times F plus G. I've almost forgot about that. G plus 2112 times F, and G is mapped to this number times F minus 1032 times G. And then it's just a question of finding the eigenvalues, and we have a linear algebra package to do that for us. And of course we could do it by hand, but that's tedious. This is not nice, but it turned out that there is an operator called rationalize that does the work. Don't know what that means, because it's not particularly rational. Well, these are the eigenvectors, and they, what gave me an idea that we could reduce it was that the norm of the denominator actually equals the numerator. So, of course, it could be simplified quite dramatically. So this is the eigenvectors. I'll write it explicitly here, the eigenvector 1. Actually, we usually write the eigenvalue here, but that would be overdoing it, I thought. Or rather, I didn't think of it at the time at all. And to find the F and G in terms of the eigenvalues, we compute the inverse matrix, and we need to simplify that. And what is rationalize didn't work, so expand was what I could do. And then we have F1, F equals this times E1. Shouldn't it be times plus this times E2? Oops, I think I've made a mistake there. E1, E2, so it's 1, 0, 1, 0. Yeah, I made a mistake here. And G, that's this times F plus this times G. So that can be written more. Well, I won't take your time doing that. All right, that was part C, finding the normalized eigenfunctions and expressing F1 and F2. Next, D, express in terms of F1 the cusp form whose nth expansion coefficient is the trace of Tn. Well, T2, we know T2 here, it has the trace (1080), and we do recognize that. No, we do not. That is 2 to 10th plus 2 to 6th minus 2 to 3rd cube of 2. I have no idea if there's a system to that. That sounds very strange. Well, so the second coefficient is 1080. And the second T1 is identity, and the second is 1080. So it should be the trace of the first one is 2. That's so we have to that's 2112, wasn't it? Yeah, out of this. That didn't quite work. Oh, it's a unity time, and this, and it should be 1080. But G, oh, it's minus 48. Nah. Now I forget what it should be. 1080. So we are 50 too high. Oh, it's 78. That makes no sense to me. So that's what we are working with, I should think. But why this should be the trace of the matrices of Tn, I have no clue. I'm missing something here, and I've no clue what it is. Yeah, I'm totally stuck. So that's it for now. Hello again. It's now 9:00 p.m. Sunday, 14th of April. I wanted to record this during the afternoon, but we had intermittent sunshine and cloud cover, so the light changed very much. I decided to wait until now. I got the eigenfunctions with the coefficient of G being unity so that they are normalized. And then we can take the matrix M, which I took from the eigenvalue. This is M, eigenvalue problem. And that gives us F and G in terms of the eigenfunctions. I think they wanted that in the problem, didn't they? Express in terms, oh, that was not needed. Well, next, when I saw this, so it wasn't wasted, then I cognited and said, we must use, of course, E1 plus E2. So I computed the coefficient of E1 plus E2, and that turned out simply to be 3,144 times F plus, that's just to prove the reduction, plus 2 times G. And we see that it actually comes out right. The T1 has, of course, eigenvalues 1, it's a double. So the trace is 2, and this one we have established. Up here, oh, it's down. Further down, we got it. Oh yeah, that was actually here we got it. So here we have the matrix, and the trace is 1080. But then we must argue that E1 plus E2 actually fulfills the condition. So that is D we are at. So they are normalized. And H of Z equals E1 of Z plus E2 of Z. We write A1Q to nth. A is perhaps not the best. Well, and then we operate with Tn on it. And Bn then equals An. The standard formula, we've had that many times. But Tn of E1 of Z plus E2 of Z, that's lambda 1 E1 of Z plus lambda 2 E2 of Z. And the first the coefficient to Q here is then lambda 1 times 1 Q plus lambda 2 Q. That gives lambda 1 plus lambda 2 Q. And that means that the nth coordinate of H itself is exactly the trace or the sum of the eigenvalues. That is equal to the trace of the transformation matrix, or of the matrix of the linear operator Tn. So that solves D. I don't know if this came out right. It was more an intuition than an understanding, but I think I have proved it. Finally, we shall compute T3 explicitly. I already started on T3 in our dry run on S12. I'll copy that down, make a break, copy that down, and then go on. I have now typed it into Maple. This was copy-paste. IQO is integer division. So n divided by 3 and discard the remainder. And I add 1 because the first node is a node. They're of course all node because we are operating with cusp forms. So I wonder why I did that really. Oh, that was because I started with M12. That was the reason for all those plus ones. Well, T3 of F and T3 of G are computed. And first we add 48G, then that vanishes. And then we subtract 94,284 times F, and then all coefficient vanish. So that is the matrix is minus 48 plus that. And we do the same with T3 of G. We got it here. So we subtract this times G. And we have got that here, so we add this times F. And that vanishes. Then we get this matrix. And the trace, that's the sum of these two guys, gives this, and it's nowhere near what I expected. So there is a mistake. Let's just check that the 8 here does the right stuff.